Good day, friends. I was talking about my PhD thesis, some contributions to two estimation problems, estimation of common mean and size of a finite population. So my PhD thesis has two parts. Part 1, estimation of common mean. Part 2, estimation of size of a finite population. I talked about part 1 in my previous talk. So today I am going to talk about part 2. So I am skipping part 1. And starting with part 2, estimation of size of a finite population. So let's start with some examples like estimation of total number of fish in a lake, estimation of total number of bugs in a code, estimation of size of wildlife in a sanctuary, estimation of total number of balls in an urn model approach. So these are the examples of estimation of size of a finite population. It has vast literature. So let's start with urn model approach. So there are several balls in an arm. There are capital N balls. How to estimate capital N? So that is the problem. So we go to capture, mark, release, recapture, CMRR scheme. It's well known in statistical literature. So what do? We capture first K balls from the urn. There are some balls in the urn and I have captured 4 of them. Then I mark those captured K balls. So I make them black. Then I release those K balls into the urn. So I put back those black balls. Now the urn contains some white balls and some black balls. Then we recapture say small n balls from the urn. Say m of them are marked. Okay, so I have recaptured 4 balls and one of them is marked. So if we count, there are 16 balls in the urn. So if we equate population proportion of marked balls to sample proportion of marked balls, we get an estimate of capital N, which is K star small n by small m. And if we put the values, our K was 4, N was 4, M was earned. So if we put them in the formula, we get N equal to 16, which matches the real life. So in reality, this is I mean, we cannot expect the estimator to work so accurately, but we admit that the estimate will be near about the true value. So the problem is what happens when m equal to 0. If we don't get any marked ball in the recapture, then it's a division by 0 problem and the estimator becomes undefined. Okay, so to rectify this error, Hossein in 1995 came up with a scheme. Pick a ball from the urn, change the color and put it back, continue the process until a colored ball reappears. If it takes small n steps to stop, then the estimate of capital N will be n into n minus 1 by 2. So one can show that it's unbiased and it's the best estimate. So in my work, in chapter 5, I completed 4 chapters on estimation of common mean. So on 5th chapter, I enhanced Hossein's estimators, compared it with existing estimators, and also studied the performance of maximum likelihood estimator of population size. The paper came out in Shankha series B in 1997 on estimation of size of a finite population. So that's an extension of Hossein's work. Now let me look at Bernoulli sequential estimation. So we have capital N in the balls and 4 of them are black, rest are white. So we go on picking up balls one by one and release them in the urn. If I get a white ball, I get 1 step right. If I get a black ball, I get 1 step up. So a sample will be a path like this. First an black ball, then a white ball, then a black ball, then 2 white balls, 2 black balls, 2 white balls. It can maximum go up to n minus k. See, if we draw the diagram a little clearly, so we have unmarked balls in the x-axis and the marked balls in the y-axis. So the sample path looks like this. And Hussein's boundary says stop sampling when m equal to 1, when you get the first marked ball. Me and my Professor Somendranath Sengupta, enhanced the boundary from 1 to n. We stop when we get m marked balls. And we did the study compared with the existing estimators, compared its efficiencies with other estimators, etc. Then we thought, why the boundaries should be straight lines? What about a general curve like this? To work on this, we needed a concept called pushed-up boundary. It's the same boundary, but pushed one unit up along the y-axis. And the result we got in chapter 6 was an arbitrary boundary. Under an arbitrary boundary, the population size is unbiasedly estimable if and only if the pushed-up boundary is closed. So if the pushed-up boundary is closed, we get an unbiased estimate of capital N. And the result came out in 2003 in the paper Sequential Analysis from Florida, Bernoulli Sequential Estimation of Size of a Finite Population. So that completes my part 2. I won't go to part 3 today. Thank you.